The title of my thesis is Imaging and Sensing in Living Cells Using Dual Modality PET Optical Imaging Probes. But that's a bit of a mouthful, and so it's easier just to think of it as using chemical molecules to look at cancerous cells inside the body. And hopefully I'll be able to give you a quick whistle-stop tour on why we need to do that, how we currently do that, and what I'm doing in the process. So first up, why? And that's simple. It's like with anything else. The earlier you detect something, the better the prospects are. How? How do we detect cancer? It's a fairly convoluted process, but it will include blood tests, biopsies, and scans. And we predominantly use PET scans to detect cancer. So what am I doing in this process? So my focus is increasing the specificity of these chemicals that are used in scans to diagnose and treat cancer. So they only go directly to where the cancer cells are and do not interact with healthy cells. So that means that when we take an image of a body, we're only lighting up the cancer cells and not the healthy cells. So a quick biology lesson. Cancer is when normal cells grow and divide in an uncontrollable way. So you can imagine the normal cells here are a patch of skin cells on my arm here, and I just so happen to have a mole. So if these cells were to become cancerous and started to grow and divide in uncontrollable ways, you would quite literally see that mole grow and stretch and distort in not normal ways. But basically that can happen with any cells anywhere inside your body, and it's just more difficult for us to see. So if we take a closer look and zoom in on just one cancerous cell, you'll see that it has on the outside, there are all these receptors, and they accept certain chemicals. And cancerous cells will have receptors that healthy cells don't. So a good way to imagine this is a lock and key. So your house key fits specifically into your door lock, and that's the same way this works, and we can utilize that. So you can imagine the grey triangle as a chemical, and it goes swimming through your body until it finds the receptor that it fits perfectly into. So in reality, these aren't actually circles and squares and triangle, and actually cancerous cells will have receptors for certain proteins or small molecules that healthy cells don't. Or, for example, cancer cells will have lots of glucose receptors on the surface, and that's because cancerous cells use up much more energy as they're growing and dividing than healthy cells, and so they require more sugar, just like you do if you're running a marathon. So here's an example of what an actual receptor looks like, and down here is the chemical that fits perfectly into that pocket. And when that chemical is slotted into place, it will light up. You can see what this looks like in the lab outside of the body and what this lighting up looks like. So this is what will be happening, this colour change, when the chemical is fitted into a receptor. And this is what it looks like under a microscope. These blue blobs here are the cancerous cells, and the green that you can see around the edge are my molecule lighting up once it is fitted into the receptor. So I think that brings me to the end of my 3-minute thesis, and I hope I haven't given nightmares of high school chemistry in the process.